There we go. So with this warm up here, I just want you to do the integral for me and evaluate it from, for number 1 to 3 of this function right here, 2x plus 1. And then I want you to integrate this one over here for me, which is the integral from 0 to pi of sine of x over cosine of x dx for me. So go ahead and do that. I got a pair deck that I want you guys to do this on. So give me 1 second here. Here we go. And then we can go join pd.com. And then you can give me the answers for these two on this pair deck. Give me 1 second here. TCR-LHO. TCR-LHO. Boom. There you go. Now, what was I saying? Extra credit opportunities in the morning. We have up until the last opportunity for the morning one is going to be until May 21st. Your AP exam will be on May 24th. So far, you have a possibility of earning 2 points out of 15 possible points towards your test. That's what these ones are going to be for your test values. That's why there's going to be limited to about 1.5 grades, right? Did I talk about that already? I think I talked about that with at least with period 4. So for you guys, hopefully you know that these extra points in the morning go towards your test score. The extra credit for the other stuff, it might go towards your test, it might go towards your homework, it might go towards your quiz score. I'm just trying to figure out what it is that you guys might need points to help boost up your grade. So I might just spread them around just to help pad them. It does make a difference because of the way actually, it might not make that big of a difference. I think this year I made them all 30, 30, 30, right? Or 33%. Hey, dog, did you want to stay in here or you want to head out? You want to go out? Okay. So you want to hang out in here and learn some calculus with me. Yeah, Angela's waiting. All right. So while you're working on that warm-up stuff, oh yes, timing-wise, we're on the last unit, and I really wish I had finished the last unit before May. I was hoping we could just spend all of May reviewing, but it's going to work out just barely. We're going to finish up our last unit probably like at the beginning of this week, 17, 18. So we don't really have much time to review together. So you need to start your reviewing on your own at this point. You either can come to after-school tutoring with me, come to office hours. Either way, you need to start reviewing the stuff from chapter 1. So the videos that I'm going to put up as extra credit is another great way to review. Like I said, Mark and Verge are awesome teachers. So if you guys watch their videos on review with them, that's also a good way to review. Some of you have gone to school and picked up the AP books that the school has ordered for you guys. I believe they're yours to keep because it's just for this school year. Like it wouldn't make sense. It's just for this year's AP exam. I don't know if it makes sense for you guys to. I don't know if you have to return them. David, you picked it up, right? Do you know if it's yours to keep? Like, did they say anything? No, they're ours. Okay, good. Awesome. So yeah, if you haven't done so, you should go pick those up. Because if you were to buy those AP books yourself, I think they cost like, I have no idea what they cost. AP review books. How much do they cost? Oh, they're not that bad. According to this, it only costs like 15 bucks. But yeah, they're free. So you should go get them. It's a free $15, right? Did I get Barron's for you guys, or did I get the Princeton review? I was supposed to be the one who ordered these, and I think I got the same one as that had like the better ratings, I think. Princeton? Okay, it's the Princeton one? Okay. Yeah, it's the blue book, right? I think it's blue. Anyways, doesn't really matter. But yeah, go get that and start doing some problems in there. They have 4 practice tests in there. Is it yellow? Oh, God, knock me. All right. Anyways, yeah, that's another thing that you can start doing. Start reviewing with that one. I'm not going to count. Should I count that towards extra credit if you guys complete the? Would you find that overwhelming, or would you find that okay if you were completing the practice problems on the AP Princeton review book? I want to. It's overwhelming. Yeah. Maybe I'll just let that go just for like Okay, the saying yes, but Monica's saying it's overwhelming. I don't want to overwhelm you. So do that if you want to do it. I do want to reward you, but yeah, I'm already rewarding you with a bunch of other things that I'm asking you to do for extra credit. So I don't want to put too much pressure on you. Yeah. Yeah, go pick up that book. That's another thing that you can do to help give you some practice problems that you can look at. Yeah, that's pretty much it. So you can see what they're going to ask and how they're going to ask it. You already have the tools to do most of these problems. I don't know if I've done a good job of getting you prepared for the way they're going to ask you those questions. I'm going to cover a couple of them today in our new chapter today, the last chapter today, which is basically just applications of integrals, right? I don't know if you remember this, but when we first learned derivatives, we learned all the rules for the derivatives. And then after we did that, we did applications of derivatives, such as position, velocity, and acceleration. So now we're going to do applications of integrals, which we'll start off with position, velocity, and acceleration, except in the other direction, acceleration, velocity, position, right, when you integrate something. So we talked about that a little bit. But anyways, let's see how you guys are doing right now on the warm-up. Let's see how you guys are doing right now on the warm-up, shall we? I have 13 of you who have clicked into this warm-up right here, this pair deck. Only 13 out of a class of 32? No, it's a class of 33? Oh, wait, it's counting me. So 32 out of a class of 32? Join in the pair deck, guys. Join in. Come on. Put the link into the chat so you don't even have to type anything. But here we go. This is what it should look like right there. So let's see what we have so far for this first one, yeah? First student here has it integrated already done. So easy. Now here, be careful with this one. This is beautifully written out, but if you have numbers here, you don't need the plus C. You don't need the plus C, right? Plus C is only there if it's an indefinite integral. For these finite integrals, you're just calculating and evaluating it from 1 to 3. So you get to just plug in these values in for x. And that's beautiful right there. If you haven't done it already, this is a perfect example of what number 1 should look like. That's beautiful, whoever did this one. Good job. Good job. Also beautiful. Also beautiful. I like it right here. Good job on this one. I appreciate the vertical line, though. That's the thing. Oh, man. And I just realized everything here is handwritten. Very nice. Beautifully typed out. Some of you guys are, oh, that one's blank, but here we go. That's another good one right there. Oh, I appreciate the brackets. I appreciate the brackets showing different symbols of inclusion. Right? Very good. Beautifully done. Awesome. Awesome. Answer. Perfect. Perfect. Answer as well. You could do U substitution. Yeah. Keep going through it. Probably don't need U substitution for this one, though, but you can. Doesn't hurt. 10 as well as the answer. Okay. So let's let me leave this up here so you guys can get this down for your own notes. Let's see here. I'll leave this one up. This one, I like this answer right here. You know what? I'm gonna just do this here. And go into here and just do this. Bam. And let's help you out a little bit here just by putting these brackets over here. There you go. Put these brackets over here. I like that. There you go. Quick conversation with some of you guys. I was grading your tests a little bit more. I haven't started making the Excel spreadsheet to put your curves in yet, so give me a little bit more time on that. But I did notice a few things that were very frustrating. I don't know how to say this other than the fact that it shows when you use apps to try to do your calc problems for you, especially if you approach something like number 2, right? So let's talk about number 2 real quick here. Well, number 1, by the way, that is the answer. It is 10. But number 2, if you look at it closely, you're probably going to need U substitution for this because there's no quotient rule for integrals, right? But sine and cosine that are derivatives of each other, so we can just go ahead and let U substitute in as one of the things. So for number 2, right, to start this off, I can let u equal to either sine or cosine. Now it's up to me. Do I want to deal with my u being in the numerator or my u being in the denominator, right? So it's up to you. I can let it equal to sine. I can let it equal to cosine. Which one do you guys want? Actually, no, that's not going to work. Wait, is it going to work? Maybe. Let's try it. Let u equal to sine of x. So then du is equal to cosine of x dx. Does this work out? Oh, a lot of people are saying let it. There you go. The cosines don't cancel out. Yeah, so it doesn't work. So I erase this out and I go the other way. Let u equal to cosine of x. Du is equal to sine of x dx. Actually, negative sine of x dx, isn't it? So good. There's a good handful of you that understand now when you're doing u substitution, it actually does matter, doesn't it? Huh. All right, so over here, we're going to rewrite this as negative du over sine of x is equal to dx, and we sub it out. Now, here's my issue when I was grading tests. So right here, I'm going to have sine of x over u, and then replace the dx with negative du over sine of x. Now, here's my issue. When I was grading, I can tell right off the bat that some students decided to use photomath and some students decided to use Mathway. And yeah, oh, good, Monica. I'll write that out and we'll get this answer out here. But here's my issue. Those programs, they do stuff, like I've been trying to tell you guys, they do stuff that is weird. They do stuff that is weird. They do stuff that is different. For example, if you use those apps, they don't show this step of substituting out and simplifying. They just jump straight from here to here. Second thing, they don't tell you what they substitute with. So those steps are left out. So when I noticed some students were turning in their work and not telling me what they were letting u equal to, instead just getting from this step to this step, it was very suspicious. Third thing, and I think this is done on purpose, those apps pick random letters to let equal to the substitution. We've always let u equal to it. So it tripped me up when I saw a bunch of them were doing t substitutions. And I was a little like, I didn't want to say anything because it's fine. If you want to do t substitution, you can use the letter t instead of the letter u. I'm not going to go in there and just be a nitpicky person about this. So if you had done that, that's perfectly fine. But you need to show it. And that's the problem with those apps. They don't show what they're letting what equal to what. If you had just written down, whoever, you guys know who you are who did this on the exam. If you had just written down t equals to something, and then dt is equal to something dx, and you did the same steps and you got what your app had shown, I would have never questioned it. I would have just said, okay, you're good. But since I saw this stuff without the work, I give points for the work as well as points for the correct answer. So those people who did that, you will be getting points for the correct answer, but you will be missing out on points for the work. So just keep that in mind. They are looking at work when they look at this stuff, especially on the free response questions. So just get yourself used to showing the work for those of you who are not doing that. Anyways, for the rest of you, especially those of you who typed into the chat who knew exactly what I needed to let u equal to, I trust you guys. I believe that you guys understand the steps and the process for doing these problems. Anyways, the integral of negative du over u, or negative 1 over u, or u to the negative 1, however you want to say it, this is going to be negative, right, ln of the absolute value of u, right, evaluated from 0 to pi. That's it. And we just plug in these values right here. We let u equal to cosine, so I'm going to sub that back out. This is the natural log of cosine of x evaluated from 0 to pi, which is going to equal to negative the natural log of cosine of pi minus a negative natural log of absolute value of cosine of 0. So we evaluate this out. cosine of pi is equal to just 1. The natural log of 1, wait, yeah, cosine of pi, wait, what's cosine of pi? Is cosine of pi 1? That can't be right. -1, isn't it? -1. It doesn't matter, Knockme. You're taking the absolute value of it anyways. Hello? Yeah. So the absolute value of -1 is just 1. So then we're taking the natural log of 1, right? The natural log of 1, right? Because we do the absolute value of it, minus, well, this is going to become plus, right? The natural log of cosine of 0, that one's 1. The absolute value of 1 is just 1 as well. The natural log of 1, if you guys remember it, the natural log of 1 is just equal to 0. So this whole thing equals out to 0, right? By the way, this is something that you're supposed to be able to do without a calculator. And if you don't know what the natural log of 1 is, don't fret and don't scratch out your answer. I kid you not. Even if you don't know what cosine of pi and cosine of 0 is, if this is a free response question and you wrote this as your final answer, they will accept that and give you full credit. They will accept that and give you full credit. In fact, on the free response questions, most professors, most teachers say that you should leave it in something that's unsimplified as long as you can type it into a calculator, even though it's not a calculator section. The graders will be able to type that into a calculator and see if it's right or wrong. So they will take that as your answer. But if you just give them 0, that they also would prefer that because, that is the right answer. But I'm just saying, either one of these are fine as long as you show the work and you get there. Okay? All right. Some of you guys might notice, by the way, that this should look familiar for some of you. The antiderivative of sine x over cosine x giving us the negative natural log of the absolute value of cosine. I don't know if you guys have seen this. I gave you guys this cheat sheet, and I should do a better job of placing it at a better spot here. Give me a second. I should put it to the front of the homepage. Yeah, I should put this on somewhere over here. But check this out. Down here where it says integral formulas on this week right here, I gave you this cheat sheet. You guys need to memorize, not all of them, just memorize some of them. But right here, the integral of tangent of x, and Monica's already pointed it out, is equal to the ln of secant of x, or negative ln of cosine of x. So this is what I mean. I never memorized numbers 16 through 19, these integrals right here. Instead, if I just understand u substitution and I understand trig identities, right? Did you know that tangent of x is the same thing as sine of x over cosine of x? So when I do that integral right here, I could have just done the integral of tangent of x dx, which again is just equal to the negative natural log of cosine of x. So if you have them memorized on a flashcard, you're pretty much done with this problem. If you don't have it memorized on a flashcard, then welcome, you're like me. You can work it out. Use the u substitution method and you'll get the same answer. It's up to you, whichever way is easiest for you. I know a lot of people who love memorizing using flashcards and they're really good at it, so they have those down. I know some people who are like me who just, I tried flashcards, it's just not for me. I mean, that's not true. I'll get them eventually, but I was very lazy. So I was like, you know what, instead of memorizing it, I'll just work out the problem. Which I know that sounds ridiculous because if you're being lazy, Knockme, then you'll have to do more work this way. And look, yeah, my brain is a little bit different in thinking that stuff. But yeah, so that's there. Okay, so get those integral rules down, get them on a flashcard, get the derivatives one as well, and get those down and get them on a flashcard and get them memorized as well. Okay, but yeah, that's that in a nutshell. All right, let's go ahead and move on here. So last chapter, okay? We're going to go on to here, last chapter. We're going to start this off right here, and we're going to start off with the applications of integrals. Applications of integrals. And the first topic we're going to start off with is, let's see here. I believe I want to do a quick connection real fast to position, velocity, and acceleration, right? Yeah. connecting position, velocity, and acceleration with integrals. Connecting all those three. So hopefully you guys remember, right? When we had something along the lines of like the position function, right? If I took the derivative of that, right, I end up with velocity, right? The velocity function is just equal to the derivative of the position function, right? And then the acceleration function is just equal to the derivative of the velocity function, or in other words, the second derivative of the position function. So you take the derivative of the position function twice, we end up with the acceleration. We did a quick talk about this, right before your exam, that if you do the integral of these things, if I do the integral of the acceleration function, that's just equal to the velocity function, isn't it? Don't forget the plus c, right? And then if we did, for the position, if I did the integral of the velocity function plus c, right, that's what the position is. So that's how we would work back and figure out your position, right, for your position function. If you do it as an integral, right, with a definite integral with numbers, I didn't get to cover this too much, but if I said I was doing the integral from 0 to 5 of my velocity function, right, this is going to tell me my total displacement. This isn't how far I've traveled. This will tell me how far away from my initial position, right? This is what this position function is going to tell me. It's going to tell me where I am located after from 0 to 5, right? It won't tell me my total distance traveled. Instead, it will just tell me my how far away I am from my initial condition, or in other words, my displacement. Have you heard that word before? Hopefully you have. Hopefully you heard it from me. If not, I did a bad job of not telling you about this. Right? Yes? Good. If you physics flashback, yeah. It's just more calculus. That's all physics is. It's not that bad. They're all connected. Isaac Newton, right? Known for physics, also known for inventing calculus. All right, so if that's the case, if this integral of the function of the velocity function from 0 to 5 just tells me the displacement, how would I calculate total distance traveled then? How would I calculate total distance traveled? If I have the velocity function, right, I want a total distance traveled, what would that equal to? Well, we know we still need to deal with the integral, right? We still need to deal with the integral, and it's still going to be from 0 to 5, right? But if I only do use the velocity function, it's only going to tell me the total displacement. So if I want to calculate the total distance traveled, right, well, what's my issue here? Why can't I just use the same thing? Why can't I just use v of t dt, right? So check this out. If I have a velocity function, right, let's say it looks like this. Here's my velocity function with in terms of time. If it just looks like this and it goes like that, let's say, then in this particular case, the displacement and the total distance traveled is the same. If I do the integral from 0 to 5, let's say, if I do this right here, up to this point right here, right? And I do the integral, that tells me this area right here, which is how far it's traveled, also how far it's displaced, right? This is perfectly fine. But for total distance traveled, if the velocity function at any point became negative, let's say the person who's traveling decided to start going backwards, his total displacement is going to be a little bit closer to it, right? So let's say the velocity that we calculate was a function that looked like this. Let's say it starts off going up, and then he started going backwards a little bit. So his total displacement, if you do this integral, right, he's traveled this far away, whatever that is. And then at this point, he started heading backwards because his velocity is negative. So he started going back towards where he started. So his total displacement is not the same as his total distance traveled, all because of this negative area down here, because the velocity is now negative and he's going backwards, right? So in order for us to fix that, we need to add this area to our point right here. We need to somehow add that area so we can calculate the total distance traveled. And the way we fix that is a very simple fix, right? If they ever ask you for total distance traveled, all you need to do is take the absolute value of this. And you'll say, oh God, I don't know how to do the integral of an absolute value problem. It varies from problem to problem. It varies from problem to problem. So some of them you try to figure out where it's going to cross into the negative axis, and then you do the integral. So let's say this is from 0 and this is 5, and I know that it crosses into the negative axis at here at 3. You would break this up. You break this up. You do the integral from 0 to 3 of your velocity function, and then add, right, the integral function, make this part the positive part from 3 to 5, calculate whatever this is, right, of your velocity function, and just make it a positive value, right? Because you know that if you do that integral, you're gonna get this negative area down here. If you make it the absolute value of that and add it to the problem, you'll be adding it to here and finding out what the total distance traveled is. And that's the connection here that hopefully you guys are seeing. When you do an integral of something, of velocity in particular, right, it'll tell you distance traveled, right? It'll tell you where is your particle going to be at, right? And if you do the absolute value of it, it'll tell you the total distance that this thing has traveled. So that's that in a nutshell. I know it seems like a lot. It is kind of weird, but we can do I can give you guys we can do a couple practice problems later on down the line. But here's what I wanted to share with you first of all. I'm gonna go put this. So don't worry if you don't have this screenshotted. I wanted to put this up on here. Give me 1 second. Where are you? You here? Did I save you in here? I think I did save you over. Shoot, where did I save you? Uh-oh. Ah, here it is. So check this out real quick. I'll put this up onto Canvas so you guys can get this yourself. But let me put this right here. God, that is huge. Excuse me. So here is like a quick little cheat sheet that kind of relates all this stuff together. So I'm going to zoom in here so you guys can see that a little bit better. But I'll put this up for you guys to have. Right? So when you have things like they tell you like particle is at position S equaling to 5 at t equaling to 0, for example, this one right here. Right? That's just a fancy way of saying that S of whatever time is equal to this value, right? So if I were to look at like S of 0 is equal to 3, that tells me that when t is equal to 0, the position of your particle is at positive 3. That's all this is. But there's a lot going on here, right? So if they tell you something like the particle is at rest, right, that means that the velocity is equal to 0 because the velocity is not changing. The particle is at rest at that point. If the velocity is positive, then the particle is moving to the right. If the velocity is negative, then the particle is moving to the left. Right? Hopefully you guys remember that. Velocity is positive, you're going forward. Velocity is negative, you're going backwards. Right? If acceleration is positive, it doesn't necessarily mean that you're going forward. I know that sounds weird. Just like as if your acceleration is negative, it doesn't mean that you're going backwards. If your velocity is positive and your acceleration is negative, think of that as you're in your car, you're going 60 miles per hour forward. If your acceleration is negative, that means your velocity is going down. So instead of going 60 miles per hour, now you're going 50 miles per hour, 40 miles per hour, 30 miles per hour. And yes, Monica, that is concave down, right? So if you have acceleration negative, it's concave down, your velocity is still positive, but it's decreasing, right? So that's the idea. If your velocity is positive and your acceleration is negative, you're still going forward, but you're slowing down all the way until your velocity becomes 0. And if your acceleration is still negative, then your velocity starts to go negative as well, right? That's the idea behind how acceleration and velocity work with each other, and all of it, how it's related to position. Okay. Average. This one's an interesting one right here. Average velocity of a particle. Right. If we know the velocity, we can take this right here. Right. The average function, the average value of a function. Right. But if we have the position function instead, you could just do this right here. If you have the position function, you could just take the slope of the endpoints to calculate the average velocity. So I guarantee you that if you come across these problems right here, there's going to be a problem like this. You need to be able to read the problem and state like, hey, what I'm given right now is position. So if I'm looking for the average velocity, I can just do this over here. Oh, hey, I'm given the velocity function. I'm looking for the average velocity. Oh, hey, I have a way of calculating the average value of a function. And it involves me taking the integral and then dividing it by 1 over b minus a. So those are small little things on there. Okay. But yeah, I'll put this cheat sheet up for you guys so you guys can write this down and have this somewhere. It's fairly neat. Yeah, fairly neat. So you can kind of see it and kind of calculate this all out. Okay. All right, I'll put this up on Canvas later today, so that way you guys can have it. Or you can just take a look on on OneNote. I don't know why I drew a blank on thinking of the name. Yeah, so if you can look on OneNote, you guys can kind of find this here already there, so you can have it if you guys want to take a look at it. Okay. All right. Some of you guys who were stuck with it with delta math on last chapter, you might have noticed the last question that was on the delta math review didn't really have to do much with U substitution, but it had to do a lot with rate in, rate out, right? And rate in, rate out is kind of basically a velocity problem. It's a rate at which something is flowing in instead of something traveling. But it's still the same idea, and it comes down to this. How well are you with your reading comprehension? And as David found out when he was with me earlier, my reading comprehension was terrible. I don't think it was a particle one. I think it just had to do with like water flowing in and water flowing out. Fish going in, fish going out. Is that what it was? So yeah, my reading comprehension was not as good either. So it was a good practice to have on there. And I just wanted to show you right here that it comes in different forms. So let me give you this example right here. Here's one of these problems that deal with velocity, acceleration, and position. So check this out right here. All right, let's take a look at this problem. This was a multiple choice question from one of the AP exams that I pulled. Okay. A particle moves in a straight line with velocity equaling to t squared minus 3 minus 7 meters per second, where t is in time in seconds. At t equals to 2, the particle's distance from the starting point was 10 meters. In the positive direction. What is the particle's displacement between 2 and 9? Between 2 and 9. Now, test-taking abilities that you have might already give you what the answer is going to be. How many of you guys have a guess right now? What do you think the right answer is? Some of you guys who have some good test-taking abilities, you might already know. No, David, it is not E. I'd like to see you try to bubble that in on a bubble sheet if there was only A through D. How would you bubble in E, David? Anyone have any guesses, any ideas? Or maybe you already know what the answer is without guessing. But if you do have a guess, let me know. What do you think it is? Read the question here. What is the particle's displacement between 2 and 9? Between 2 and 9. Now, my initial guess, Monica, Brian, good stuff. Now here's the issue. They give you this random piece of information right here, right? They give you this random piece of information telling you that at t equals 2, the particle distance from the starting point is 10 meters. So initially, I kind of want to go with this one, right? But this is not the answer. That's because this is going to tell you the particle's displacement from t equals 0 to t equals to 9. How do I know that? How do I know it goes from 0 to 9 right here? Not from 2 to 9, even though the integral is from 2 to 9. Why is it from 0 to 9 for this particular example? Anybody tell me? What is it that's causing that? And the answer is going to be B, by the way. But why is it not A? Why is it not A? Any ideas? No, nothing. We know that this one is going to be total distance traveled, right? That's not what they're asking for, and this is still total distance traveled. They're asking from 2 to 9. Yeah. That plus 10, right? This right here is from 2 to 9. If you put the plus 10 with it, the plus 10 includes that initial starting distance. Does that make sense? It's how far away it was at t equals 2. So it's not going to be that one. It'll just be B. Okay? So that's the idea. If you know the connection between your position, your velocity, and your acceleration, this one was, hey, here's the velocity. I need to find out the position that it's traveled, right, or the displacement of this particle. You have to remember that, oh, just do the integral, right? Because position is just one level above velocity, right? It goes it goes position, velocity, acceleration. So keep that in mind when you are doing these problems here. All right. Reading comprehension stuff, I wanted to do this example with you guys, and I want you guys to try this as well. I'm going to turn off student pace on the pair deck. I'm going to ask you guys to go to the third slide. And there is this right here. I'm going to put this on my screen so we have this together here. So let's go ahead. Let's copy that. Let's see if we can fill this out. I want to give you guys a couple minutes to try to fill this out as best you can. There we go. So in this case, position is written as x of t instead of s of t. Right? A particle is moving along the x-axis in feet from the origin, and it's given by x of t. The velocity of the particle in feet per second is given by v of t, and the acceleration is given by a of t. For each of the integral expressions given in the following table, interpret its meaning by filling in the missing noun, appropriate units, and or the correct time value or interval. So, for example, right, we talked about this one over here, this absolute value problem right here, right? Absolute value of the velocity from 1 to 4 is going to tell me what? It's going to tell me the total distance traveled from 1 to 4, right? What's the units of this thing? This is going to be in feet. And it's not even from the origin, right? This is just how far, this is just the total distance traveled. I don't know how far away it is from the origin. But that's it. That's all I would put down for that one right there. So can you guys fill out the rest of these for me onto this pair deck? And if you have closed out the pair deck, let me open this back up so you guys can get the credit for this for today and checking these along the way. So see if you can figure out what the other ones mean. What do they in turn? What do they tell? What can you figure out from this? A couple of them are probably like, you might be able to tell they're averages, aren't they? Aren't they? Mm-hmm. 。 Okay, a couple of you have gotten a couple more answers, and they're good. Just try it out, see what you get. Don't wait for me to do it. Try it. And then when you see what you get right or wrong, then copy down the right answers for your own paper. All right. All right. How'd you guys do? Let's see. Couple blanks, which is okay. Couple filled, which is also okay. Not bad, not bad. All right, all right. Let's take a look here. Easiest one for me to go, I kid you not, easiest one for me to go is always the one where I see this fraction involved, because I know that this right here, whenever I see this fraction here that involves the a and the b, in my mind it automatically goes to average. The average of the function that you're dealing with, right? So for this particular problem, this is the average and I look at the function. My function there is the velocity. So I can say it's the average. Well, it's not actually the average velocity, is it? It's the absolute value of it. So and this is a little bit of a catch, like a little bit weird thing. It's not the average velocity, because velocity can go negative, right? And if you do the absolute value of that, you're looking at the average speed. The average speed. Speed and velocity are a little bit different. Speed and velocity are a little bit different from each other. It's not the distance, though, right? It's not the distance. When you do the integral of the velocity or the speed, it does give you distance. But this is the average speed, because we're just dealing with the velocity itself, because of that fraction that's in front there, right? That fraction that's in front there. So we're doing the right here, the average speed of the particle. Right, average speed of the particle. And take a look at this. If it was distance, the units would not be feet per second, right? The units would just be in feet, right? The average distance, right, would just be in feet. But this is the average speed, which is in feet per second, which is going to be from t equals 1 to t equals to 4. There you go. There you go. Okay. All right, let's fill out the one above it here. This one right here, the integral of the derivative of the position. Well, isn't that just the integral of the velocity? Right? Because the derivative of position is just the velocity. So what's the integral of the velocity from 1 to 4? That's the change in position of the particle. This is going to be in feet, right? Because it's just the position. Position is just in the units that you're measuring in distance, right? So in this case, it's feet. Sometimes it'll be inches, sometimes it'll be meters, right? But when is this happening? This is happening from t equals to 1 to t equals to 4. That's all that is. The first one, this one looks fairly strange, but if you remember back to the multiple choice question we just did, right here, right, this is the total displacement, right? The displacement from 2 to 4. But if I add the initial value of this, this is telling me the position of my particle. The units for this one is going to be in feet. But since we're doing x at 2 from 2 to 4 for the integral, it's in feet from the origin. It's telling me how far away it is from the origin when t is equal to 4. How far away is it? That's all that is. From the origin. This one is a little bit of a tricky one right here. I'll put that one last. This right here, again, I'm telling you, if you look and you see this right here, my mind should automatically go to average. You see that? And what's the function that we're dealing with? We're dealing with the acceleration. So this is the average acceleration. And you guys probably have the time already. This is from t equals 1 to t equals 4. Who's got the units for this? Who knows what the units is for the average acceleration? What would that be? Feet per second squared. That's it. In feet per second squared. That's it. That is it. You guys might not realize it, but the one that I starred looks fairly close to this first one right here, which is still going to be the position of the particle. Position of particle. It's again in feet from the origin, but who's got the guess for this one? This is going to happen at t equals to what? Who's got the guess? It's t equals to 2. Very good, Monica. Good. Yeah, you're catching on. Well, you're catching on that the fact that this one's going backwards, isn't it? Well, you can do that, by the way. You can go backwards if you know where it ends up after, right? If we just reverse it, it's going to subtract. That's going to come out as a negative integral, and it's going to subtract from where that is. But yeah, knowing how to do integrals now is awesome. You got use substitution, you got different rewriting techniques, and you have these other things memorized. But now that you know that, the hard part of calculus is they're going to ask you these questions, and you need to know, do I take an integral on this problem, or do I take the derivative on this problem? And in calculus, those are really the only options. You either work with the function you have at that point, you know, and just plug in the numbers and see what you get at that point. Because if they give you a position function, and they ask you how far it traveled, you can actually calculate that just by plugging in the number and see how far it is. But if they ask you for velocity, and they give you position, your brain needs to click and realize, I need to take the derivative of this thing to figure out what the velocity is. And if it goes the other way around, hey, I'm giving you a velocity function. Can you tell me how far away it is from the origin? Your brain needs to click and say, integral of that problem. Okay? The functions itself will be things that you need to know how to do using chain rule, quotient rule, if you're doing derivatives, use substitution if you're doing integrals. Those are stuff that's on the side. Like that, those are techniques that they're going to test you on. But before you even get there, you need to know that that's what you need to do. Okay? And they word things in really weird ways. They word things in really weird ways. And this is one example I wanted to show you right here. Let me go ahead and open this up. Let's go ahead and move on here. Let's go and talk about the next section right here, which is going to be integrals as accumulation functions. You'll probably say accumulate what now functions? Accumulation functions. How are we doing on time? We're doing okay? We got like 20 minutes? So let's say I have something like this. I had a rate of change right here, and I was, instead of dealing with velocity, which that's the main thing, position, velocity, acceleration, if instead of that I was dealing with a printer, okay? Suppose that a printer, let's see, which one did I get there? Did I get this one? Yeah. Suppose that a printer was rated at 8 pages per minute use a graph to show how many pages would be printed in 5 minutes. By the way, what would that be? What would the answer be? If a printer is printing at 8 pages per minute, how many pages should be printed at 5 minutes? 40. Yeah, 40. That's a silly question, isn't it? You guys are like, yeah, that's easy. Hello? Right? So it would look something like this, right? If it's asking us to use a graph to show this, right, we can kind of show this easily, right? Something like that, right? And then this is, of course, is going to go as a function of time, right? And then this is the number of pages that come out. Okay, this is the number of pages that come out. So it looks something like this, right? Actually, no. Here, we were graphing in pages per minute, so let's go with the rate, right? Rate of pages per minute. So it's printing at 8 pages per minute. So here we go. Let's go by 2s here. 2, 4, 6, 8. So right here, it's printing at this constant rate right here. And we go from 1, 2, 3, 4, 5 right there, right? This is the rate at which it's printing at. Now check this out. You guys already told me the answer is supposed to be 40, right? Do you guys see 40 visually anywhere on this graph? Like, how could I show like 40 with this graph right here? And Brian's going, it's the area, right? It is the area. If I were to look at this area right here, that will tell me the total number of pages that have been printed, the area of that rectangle. That's right. That's right. And we already know something about calculating area, don't we? We know that when you calculate area, right, it's technically just the integral of whatever function that you have. This function right here, right, this rate, let's call it R of t, the rate at which pages are being printed, is equal to 8 pages per minute. If I do the integral from 0 to 5 of that function, this right here will give me this area, which happens to be 40. Now, if you actually work this out, this is the part that's cool. It all connects. If this is my function is 8 of t, check this out. Doing this integral, that's going to equal to, sorry, foot cramp, foot cramp, foot cramp, stop. Stop it. Sorry. So if I do that right there, right, this is the integral from 0 to 5 of 8 dt. That's going to equal to the same thing as 8t evaluated from 0 to 5, which of course comes out to be 8 times 5 minus 8 times 0, which of course is just equal to 40. Now you say, knock me, why would you go through all this process when you can clearly just look at that area? And I agree. That's the main goal of it. But what I want you to understand is, right, 40 pages, of course, is understanding the connection here. We can start doing the same stuff for various rates. It could be the rate of how much fish is being put into the ocean. It could be the rate at which how much sand is being washed up on a beach. This is the rate at which a printer is printing pages, right? If you know the rate of it, you can actually accumulate and calculate the total of something it does over a specific amount of time. And it's kind of neat. It's kind of neat. A little bit different, but it's kind of neat, I'd say. So if I had, for example, of my rate was a really weird looking function, right? Let's say my rate was a function that looked like this, instead of like a simple just 8 pages per minute, right? It was instead like a varying function, like let's say here. Suppose that my rate was this guy. It's printing at a rate of 3 times sine of pi over 2 times t plus 5 pages per minute. Sketch the graph. How would you find the total pages printed over 5 minutes? So let's see here. For something like this, this is usually going to be given to you on a calculator section. Whenever you see something like this and they want you to calculate the rates of it, this is usually something where you're going to need to use your calculator. So let's open up our calculator and take a look at this graph here. How would I graph this function on my calculator? First of all, you got to turn on your calculator, knock me. How would I graph this function? Just a quick refresher. Do you guys remember? How do I graph a function that I need to deal with here? get yourself familiar with this calculator. It is going to be available for you during the AP exam, so please make sure you are familiar with it. So if you're given the function like this and you need to graph it, right? Math the 9. Oh, that's going to give you the integral. Oh, you're already ahead of me. You're solving for the area underneath the curve. But before we do that, let's see if we can look at the graph of this thing first. Okay, let's see a look at the graph. So Monica's saying doing math 9 for those of you who are following along. This will help us to integrate this and calculate it. But before we do that, let's get the graph of this thing. So I don't know if you guys saw, to get to that part, let's clear this out. To get to the graphing part, press the y equals button on the upper left of your calculator right there, y equals, and you get to enter in your function. Now, please understand R and T are all dummy variables here. Your calculator works with y's and x's, so switch out the t's with the letter x here. So instead of r of t equaling, it's going to be y equaling to 3 times sine of pi over 2 times t. So be careful with this. I like putting parentheses just to make sure that it keeps things in check. Pi over 2 is going to be done on its own, times t. Close that off, and of course, put a plus 5 at the end. I need to see what this graph looks like, so I'm going to go ahead and graph this. So it's printing at an interesting rate. Right? It's printing at an interesting rate. Now, I don't really care about the negative values because there's no real negative time in this one, so I'm looking for everything above. I'm looking to see how much pages were printed over 5 minutes. I'm assuming the first 5 minutes. So I'm looking from, if I need to adjust my windows, if you guys know how to do this, there's a window button right here. And you guys need to be able to work with this because sometimes when you graph things, it'll be out in the thousands. It'll be printing out like thousands of pages. And you need to know like where it fits. You can adjust your window here. So this right now is going from -10 to +10. I don't really need that many negative values. So I'm just going to have it go from -1. Or you can even go from 0, right? And I'm not going all the way up to 10. I'm only looking at 5 minutes. So I'll go a little bit past 5 minutes. Let's go like 6. So let's go from -1 to 6. And the y values, it didn't look like it was negative at all, right? So I'm going to put here, again, I'm going to put -1. You could just put 0 if you want. I'm going to put -1. And the y max, it didn't look like it was going that high, but I'll leave it at 10 for now because I forgot what the high values were. I go ahead and hit graph now. As you can see, I can adjust my window so it's easier to see. Now, I'm a person who's adamant about using Desmos when you can. On the AP exam, you're not allowed to use Desmos. So on Desmos, it's easy. You just click and move your window around and zoom in and zoom out where you need to. You can't do that with the TI calculators. You can't just touch. It's not a touch screen. You can't just slide things around. So you have to kind of like know how to adjust your window size so it's something that's easier to deal with. Right? So we have our function right there. So if I take this function, right, and I take a look at it, what you're essentially doing, right, when you're calculating for the total pages printed, you're essentially calculating the area from 0 to 5, which is right here. So I need to calculate this right here. And if you're looking to just calculate this area, right, because this is the rate at which it's printing, and I'm looking for the total pages printed, all I got to do is take this integral from 0 to 5 of 3 sine of pi over 2 t plus 5 dt. Now, you can do this actually. You can do this integral by hand. I believe you can, right? Integral of sine is just cosine. You need to chain rule. You need to use substitution this out. I think you'll be able to do it. But I want you to practice doing your integrals on this calculator as well. So today, let's take a look at that and see if we get the right answer. So to get out of your graph, by the way, you just hit second and then mode. It'll quit you back out to the main screen. And as Monica was saying earlier, to do integrals on your calculator, we just simply hit math, right? We go over to option 9, which let me actually show that step. So if we go down to option 9, you can see it. It's called fnint. Fnint. Okay, fnint. So we go here, and we start plugging in the values. This is going to go from 0 to 5. And then inside here, I just plug the function. I already plugged in this function, the y sub 1. And if you're getting comfortable with this, check this out. I can actually just do this. You ready? If you hit alpha and then trace, it brings up this menu. And look at here. It has y1 all the way to y0. y1 is where I placed in my function to graph it. I can press enter like that. So this will actually type in the same function I have stored in y1 without me having to retype it. It's a nice little shortcut. This, of course, is in terms of x's. I know some of you guys are like, it's in t's on this paper, but remember, this is a dummy variable on this calculator. We can put it in as whatever we want. And that's going to be our answer right there. If we had done this by hand, you could probably get the same answer, but then you'll have it in terms of pi. Okay, so applications of integrals. It not only can tell you like position, velocity, acceleration, it's a new way of connecting those old things that we already know, right? We also have ways of dealing with rate problems now. So if you remember related rate problems, you can figure out how fast something is falling away from each other. I don't know if you guys remember, it was like those problems where a skateboarder is going north and another skateboarder is going east at these particular rates. What's the rate at which the distance between them is closing? So you get like a negative something because they're getting closer and closer, right? Or if they're skateboarding away from each other, their distance is a positive rate that's getting further and further away. Now that we have those rates, we can actually calculate totals of things. And it's not just distance now. It's also pages of things. It's also, I'm telling you, it's like the most random things that have rates that you can figure out. From the Delta Math review, David, correct me if I'm wrong, was it like number of fish being put into a lake and then number of fish that was being taken out of a lake or something like that, right? No, it was water? Oh, that's even easier. It's the amount of water that was being pumped in and a number of amount of water that was being leaked out, which is a very common thing as well. It's like you're filling in your pool and your pool is leaking at this amount. I meant fish on my cursor. Oh, that's what it was. But yeah, so that's the idea there. So what I want to do right here is take a look at another example right here. Let's see here. We've lost a couple students, it looks like. Julia's gone and Alejandra's gone. Just double checking attendance. Francisco never joined. Okay. All right, so let's take a look here. This is from the AP free response question from 2010. All right, let's take a look at this one. So from 2010, let's take a look at this question right here. We're not going to have time to finish this, but it's a good one to look at. Give you guys a second to copy this down. It's quite a bit. This was in the calculator section of the free response. There is no snow on Janet's driveway when snow begins to fall at midnight. From midnight to 9 a.m., snow accumulates in the driveway at a rate modeled by f of t equaling to 7 times t times e to the cosine of t, cubic feet per hour. So this right here, if you want to connect it to something in your mind, it's the rate at which snow is falling, which is kind of like your velocity. It's not the total amount of snow that's there. It's not the total amount of distance that you traveled. It's the rate at which snow is starting to fall. It's the rate or how fast you're going, right? It's just the rate of your problem. T is measured in hours since midnight. Janet starts removing snow at 6 a.m., t equaling to 6. The rate g of t in cubic feet per hour at which Janet removes the snow from the driveway at time t after t hours after midnight is modeled here. So from 0 to 6 a.m. she isn't removing any snow yet, right? So it's 0. From 6 to 7 she's hauling, but she's removing 125 cubic feet of snow per hour, and then she starts to slow down after that hour down to here. So she got a little bit tired, so her rate at which she's removing snow has slowed down to 108. Right? So think of this in your mind, right? Both f of t and g of t is the rate at which snow is supposed to be on that curve. F of t is the amount of snow that's being added to the curve because it's falling onto it. G of t is the amount of snow that's being removed because Janet is, shoveling the snow out of her driveway. So she's removing that amount of snow per hour. Okay? Now, looking at that, right? Knowing what is being given to you, they ask you multiple parts of these questions. And the first part is, how many cubic feet of snow have accumulated in the driveway by 6 a.m.? How would I figure that out, guys? How would I figure that out? How much snow has accumulated on the driveway by 6 a.m.? Anyone? Anyone have any ideas? F of t is how much snow is falling onto the driveway. G of t is how much snow is being removed. But from 0 to 6 a.m., none of it is being removed right now. Any hints, any clues, any ideas? Don't overthink this one, right? I know how fast the snow is falling onto there, and Brian's got the right idea. I'm looking at it from 0 to 6 because it's by 6 a.m., right? And we're looking at it from midnight because there was no snow before midnight. So I'm looking for the integral from 0 to 6. Now, which function? Brian's already saying it. He's saying it's the function f of t. And Brian, you are correct. F of t dt. Why is it of f of t? F of t is how much snow is falling on there. Now, if it was going to say from 0 to 7, I would do this right here, right? It would do the same thing, but go from 0 to 7, right? But then don't forget to subtract the integral from 0 to 7 of g of t, the rate at which snow is being removed. But it's not asking that, right? It's not asking at 7 a.m. Because once 7 a.m. comes around, from 6 to 7, Janet starts removing it. So I need to remember just to remove that snow at this particular rate. But that's not the case in this one. This is going to be from 0 to 6. And you just plug this into your calculator, right? Same thing. Let's go to our calculator and practice plugging this function in, this integral in. All right, so this is going to be math, option 9. It's the integral from 0 to 6. I don't have this function saved in there, so I need to type out this function for my calculator. So it'll be 7x e to the cosine of x. Man, that's a monstrosity of a problem, isn't it? Dx, and that's it. You just plug it in like that. We don't need to worry about doing the u substitution or anything like that, and we get our answer, which is 142.275. 142.27. It rounds to 5. It's 7.4, but that's 6 after. I'm going to round it to 275. Who's got the units for me? Who's got the units for me? This is 142. What? 142 snow? It's cubic feet. Good. Good. Cubic feet. If a problem specifies that you need to put down the units, you need to put down the units. If a problem does not specify that you need to put down the units, don't put down the units unless you know for sure. I know this sounds weird, but if they don't specify the units and you put down the wrong units, they take a point off. If they don't specify the units and you don't put any units, you get the full credit if you get the answer right. They don't care what the units should be if they don't specify it. So read the problem, make sure it doesn't specify that you need to include units. Most of the times they don't. So leave the units off of it unless it specifies the units. It's just an extra thing that you don't need to worry about that you don't need to freak out about. Okay? All right. I got a couple minutes left here. Here's what I want you guys to try to figure out. And I'll leave this pair deck open for you to do this. I will count this as your first homework assignment into this unit here. So this right here is going to be from these parts right here. I want you to get these 3 things for me. Okay, these 3 things. Part B is to find the rate at which, find the rate of change of the volume of snow on the driveway by 8 a.m. That's the first one up. Part C here is let h of t represent the total amount of snow in cubic feet that Janet has removed from the driveway at t hours after midnight. Express h as a piecewise function. I don't know if I want you to do that one yet. No. Put that one on hold. Put that one on hold. Do B and do D for now. No, that's not good. You know what? No. Forget doing that on the pair deck. Forget doing that for homework. We're gonna go over this together. I think you guys might be able to do B, but for part C and part D, I think we should go over that together. Yeah. I was thinking that you guys could do it, but it is the wording of that's a little weird. So we'll put that on hold for now. So actually, you guys might be able to do it. I shouldn't hold you back. Just try it. We'll go over it together, though. But I think I'm going to stop here for today. This problem is going to be up for you guys to try. Yeah, and then we're going to get into the other application stuff on Thursday. All right. Just a heads up, I will be on campus today for after-school tutoring. So if you guys want to sign up. Oh, can you change? Oh, whoops. Sorry. You are right. Or here, student paste. Got it. There you go. Okay, so I will be on campus today for tutoring after school. If you guys want to stop by from 3 to 5, please sign up. if you haven't done so already, I need a couple of things before you go. I've changed my office hours from 1 to 2. It is now from 2 to 3. That's due to the fact that I need to give myself some time to drive on campus, because I'm not. I don't know if you guys can see that I'm not teaching on campus right now. I got lazy and I don't want to wake up early anymore. So that sounds bad. But here's the thing. So office hours are from 2 to 3. That way it gives me time to drive to school. And here's the other thing. If I don't see any names signed up on the after school sign up by 12 o'clock day of, I will not be there. So I checked for Tuesday last night and I saw that I have a student signed up. I have one student signed up for today, so I will be there today. Yesterday I saw no one signed up, so I wasn't there after school. So Wednesday tomorrow, if this stays blank by 12, let's say 12:30, I'm gonna be checking this by about 12:30. If I see no names signed up by 12:30, then I will not be hosting a after-school tutoring session. I will be there for office hours like normal online from 2 to 3, but I'm setting the timeline now for this one. So if you don't sign up for it by 12:30 day of, then I'm not going to be, if there's no one there, I won't be there. But if you see someone's name on there, that means I will be there, and you can put your name on late if you want. But don't be late. Just put your name on there earlier, so that way I know that you're going to be coming. Okay? Only put your name if you're for sure going to show up. Okay. All right. Other than that, that's it, guys. It's 10:37. Have a good rest of your day. I'll see y'all on Thursday, unless I see you sooner at tutoring. All right. Bye, everybody. So long. Farewell. See you later.